morning, everybody. Thank you for joining us. Today, I'd like to talk over the new features that are in the Armv8.1 processors. So to put that in a little bit of context, all of the ARM Cortex-M processors sit within specific architectural revisions. So the M3, M4, M7 sit within the Armv7 architecture, so that the code between them or the instruction set is compatible between the processors. The existing smaller processors, so M0, M0 Plus, sit in Armv6, whereas the newer M33, M25 sit in the Armv8-M extension. So within all of those revisions, the code is upwardly compatible. And today I want to have a look at the Armv8.1 processors, which introduce a new range of features. So the most important amongst these are the Helium vector extension. So this gives us a big boost in maths performance, particularly for security, cryptography, DSP, and machine learning. It also introduces some extensions to security, so particularly the pointer authentication codes, branch trace checking, and also monitoring of the processors through a performance management unit, and the reliability, accessibility, and serviceability extension as well. So some very important new features on these new processors. And within Armv8.1, there are two new processors that have been announced. Cortex-M55, which has been licensed by a number of silicon vendors, and the silicon now real microcontrollers are starting to come onto the market. The Cortex-M85 was announced last year, so devices are still in development, and I think there's been some demonstration of early silicon, particularly at large trade shows such as Embedded World. So again, we've got real processors that are either emerging or should be with us in the near future. So to look at the big difference, certainly for Cortex-M55 initially, is its performance for machine learning and DSP. So here with the yellow bar, we can see that there's a huge boost in performance through the vector extension. So this gives us about 7-time performance for some machine learning algorithms. So, for example, recognizing the CIFAR 10 dataset, which is a bunch of thumbnail images for 10 different types of objects. So this runs convolutional neural net, and here we're seeing a boost of about 7 times performance over a Cortex-M4. And for keyword spotting, we've seen about a boost of 8 times. So this is a huge uplift in performance for just a standard processor. And then moving on for the Cortex-M85, we can see there's an additional boost for machine learning and DSP. And compared to the Cortex-M7, running our sort of traditional embedded code, we're also seeing the Cortex-M85 will be the highest performing Cortex-M processor. So again, these are two new important processors for just overall improvement in the ability to process DSP machine learning, but also very good for traditional embedded code as well. So as I mentioned, one of the major additions to both of these processors is a vector processor. So this gives us a whole bunch of additional new instructions, so over 150 instructions, and it's particularly aimed for advanced mathematics as well. So currently within the existing floating point unit, we have a group of up to 32-bit registers. So this will hold single precision floating point results. In M7, we can also make this double precision. So this will give us 15 registers that are 64-bit wide. But with the addition of the vector processing extension, we can now arrange those registers as 128 bits wide with 8 of these vector registers. And these vector registers can now hold integer values, so 8, 16, 32-bit integer values, as well as 32-bit or single precision floating point, but also interestingly, the vector extension introduces half precision floating point as well. The integers can also be held as Q numbers, so this is a fixed point notation which is commonly used in DSP algorithms, and is also used in the Arm DSP library, which is an open source library that's free to use. And as we'll see later, that library has already been provisionally adapted to use the vector extension. So we have optimized DSP algorithms ready to use for this new hub. So these 8 vectors are arranged, and each 4-bit element of the 4-byte element of the vector is arranged as a vector lane, so that we can process values held in each 4-bit lane, 4-byte lane, and these can also be conditionally executed as well. So again, this gives us quite advanced ways of running our DSP algorithms, etc. In addition to supporting integer and floating point, we can also perform complex maths on these, and there's also support for big integer support. So these are very large numbers used in cryptography, so we can process 128-bit or larger numbers within a vector lane as well. When we're processing these instructions, the data path to the vector extension is 64 bits wide, so a 128-bit vector can be processed in 2 beats or 2 processor clocks. So down in the bottom right-hand corner, you can see the data quantities that we can process per clock cycle. Additionally, it's a pipelined processor, so that the load and store instructions can be overlapped in the pipeline as well, which further increases our performance levels. Now, in terms of the processors, we have a greatly enhanced instruction set. So we saw that within Armv8, there was additional instructions to support the TrustZone extension, and also to allow the processor to support some of the newer C standards as well. So within Armv8.1, we have additional sets of instructions to support the new processor features. And in addition, there's some interesting groups of instructions that have been introduced. For example, low overhead branching, as I mentioned before, the half precision floating point as well. So in terms of the low overhead branching, in the earlier Cortex processors, when we had a loop within our code, we had to have a branch test, which was executed every time we go around the loop. So with the Armv8.1, we have a while loop start instruction, and here we can load up the number of times that we want to go round the loop. So we only execute the 2 instructions at the head of the code here once, and then the body of the loop is then automatically executed n number of times before exiting. So this removes continually having to test and exit the loop. There's also a do loop start, which where we're processing data that's in the vector extension, if that doesn't fit in the vector lane width, so for example, we have an extra element, there is a while loop start tail prediction that means we can process the final element of the loop automatically without having to have any additional kludgy code. So this whole group of features gives us very efficient looping instructions that in a standard code are going to produce some quite good improvements in performance. Additionally, we have groups of additional instructions which will do a lot of conditional increment, decrement, setting, clearing of bits, etc. So again, these are good general purpose instructions that will overall increase the performance of our code. In terms of the security features, we have pointer authentication. So that one of the big problems that we face if we put any of our devices online is that they're very much open to software attacks. These generally take the form of return-oriented programming or jump-oriented programming. So this is where an attacker will attempt to use a buffer overflow technique to corrupt a pointer or corrupt a return address. And then they can gain control and start to run malevolent code on your target. So the pointer authentication code is a method of signing the return address when we call a function, and we can then verify that return address to make sure that somebody hasn't tried a return-oriented programming attack. Similarly, for indirect branches, we can do branch target identification, where we can jump to a target, and if we don't land on a correct instruction, we know that the branch has been interfered with. So this will then prevent jump-oriented styles of attacks. So with the pointer authentication code, when we when we branch to an instruction, we can sign the pointer. So this is, we take the pointer, we take a modifying code, which is typically the stack address. So we extend these two to a 64-bit value, and then we can run that through a lightweight cryptography algorithm, which we must provide a 128-bit key, and this will then give us a signature for that return address and stack pointer value. We branch to the function, and when we return, we can then recalculate that signature, and if it doesn't match, then we know that somebody has interfered with the return address through, for example, a stack attack. So this gives us a very solid way to stop common hacking methods at source. So there are also a number of keys for the secure and non-secure mode, privileged and unprivileged modes. Each have different pointer authentication keys. So again, if an attacker does manage to access one key, then he still can't fully exploit all of your code. Similarly, for branch target identification, there is an additional bit that's added to the program status register. And before when we make a jump using branch target identification, we set this bit. We then have to land on a specific clearing instruction, which will then clear down that bit. If we land on any other destination instruction in the code, then we will generate a fault. Here, this will stop any kind of jump-orientated attack which has managed to corrupt a pointer extension. As with the Armv8 processors, Armv8.1 has TrustZone fitted. So this is a security extension which allows us to split the code, data and peripherals into different secure and non-secure regions. So this allows us to place our sensitive data and functions in a secure, isolated area of the chip, so that we can jump over the isolation barrier and run the secure code, an encryption algorithm, and then return back to our application code, which is running the non-secure region. So Armv8.1 has made some improvements to the FPU context management here, so it runs more efficiently, but has also introduced a mode of unprivileged debug. So normally, if you're debugging in the non-secure code, you can't see any of the code in the secure region. So with the unprivileged debug extension, we can have our secure region, which is generally split into a partition manager and then various security services. And we can install our own security service in the unprivileged region of the secure world. So we can then allow debug of that code from the unprivileged region. So as our code moves between secure and non-secure code, we can debug all of our application code. So this is quite an important improvement, and it allows you to selectively debug all regions of your code. Now, within the earlier ARM7 processors, we had a number of performance counters, which I think probably most people weren't particularly aware of or weren't particularly used for debugging in general, but they would keep track of things like sleep cycles, number of interrupts, interrupt entrance and exit. And within the Carl debugger, some of these values were used within the system analyzer so that we could get a trace of interrupt activity. But all of this, I think, was probably a bit transparent to most people using the Cortex-M processors. Within Armv8.1, ARM have added a fully fledged performance monitoring unit that puts out a lot more information about the performance of the processor. So here we can get a lot of statistics and interesting information run out through the trace pipe. So this will, pardon me, allow us to extend the debug support to give you a sort of a trace of all of the processor events, so you get a much deeper view from within the debugger. And again, these will be able to be selectively enabled and disabled so that you can fully optimize your code and see exactly how it's running on the processor. In addition, like the M7, there's a number of error correcting code support built into the memory and cache so that we can do single error correction, double error correction, and also fault reporting. Now, because we have a cache running within the Armv8.1 processors, there's also a poison signal, which I'll discuss in a moment. Within Armv8.1, like the Armv8 processors, we have a new memory protection unit, and this has been extended to have a new privilege execute never condition, so that we can switch off execution of unused privileged regions of memory as well. Now, within the ECC support, we may have data get corrupted within a cache. And this will cause that data to be evicted back to the memory. So we're evicting the data plus the fault into the main memory. And at this point, we are then setting a poison signal on the AXI bus. So when the code next comes to access that data, the actual fault will be raised when it tries to access it. So this means that the fault is raised synchronously with the code that's trying to execute or trying to use that data. And that makes it much easier to deal with the corrupted data. If we raise the fault when the data was corrupted in the cache, the processor would be running a different area of code, and it would be much harder to work out what was causing the fault or what the problem was. So the ECC codes and the poison signal allow us to more efficiently deal with corrupted data. And then events within the ECC memory are reported through the reliability, availability, and serviceability peripheral that allows us to monitor how the code is executing on the flash, and if there are any faults within the memory or the processor. So this stores records within the processor that we can monitor. So if there is a memory fault, we can read and detect it and then respond to it. So this allows us a method of checking that the processor is running correctly, and we can detect any errors or degradation in the processor. Additionally, the Armv8.1 has full support for the various methods of using a coprocessor. So within the earlier ARM processors, the coprocessors were memory mapped, and within Armv8, they were moved to direct coprocessor support. Within ARM 8.1, we now have custom instructions which basically tightly couple the accelerator to the CPU. So if our memory mapping to, for example, 4 instructions to access, coprocessor takes 2, the custom instructions then take 1. So the performance has again greatly been increased for hardware accelerators and coprocessor support. Now, in terms of using all of these features, the compiler, the ARM compiler is designed to support auto-vectorizing. So once we enable this, and we need to be optimization level 2 or above, and then we can enable vector extensions for both integer and floating point, and then the compiler will automatically optimize your code to make use of the vector extension. So again, this support for this is directly under the hood. We can also use optimized library. As I mentioned earlier, there's a DSP library from ARM, which is optimized to use the vector extension. And there are also a number of macros available so that you can hand optimize code if you want to as well. We can also enable support by changing the C language to support half precision floating point. So this is supporting C11 or C++. And we can enable the pointer authentication code support through command line options as well. So we have branch protection, and we have various levels of options there to support on by either the pointer authentication code or branch target indication. So again, this will we can either do this at a module level or down at a function level as well. Within the various CMSIS standards, they've also been extended to support Armv8 and Armv8.1. So CMSIS core has additional NPU and TrustZone functions, and as well as the performance management monitoring unit extension as well. As I mentioned, CMSIS DSP is extended, but also the CMSIS neural net, which sits on top of CMSIS DSP, has been extended to support Helium as well. So again, much of this is available now. And so I forgot to mention, there are also ARM virtual hardware models, so simulation models that are available for Cortex-M55 and M85. So testing and porting of software is possible now, even without having real silicon available. So in summary, we have 2 new processors that should be with us imminently. In the case of Cortex-M85, probably about the next year or so. They're going to give us a big improvement in maths performance, enhanced security options, but they retain the same programmers model as the earlier Armv7 architecture, so that we can move our code and our existing knowledge onto these processors very, very easily. The development tools and support is largely here already. So again, we'll be able to take advantage of these hopefully in the very near future. So if you have any questions, please raise them and I'll come back to you. Again, thank you very much for being with us today.